Yes, and partial also, because of course I cannot cover it all. So good afternoon, everybody. Is this what you want in terms of size, or had you had hit a better configuration? Otherwise, I'm happy with this. I don't mind. Okay, I start anyway, and then we see what to do about the screen. So, indeed, good afternoon. It's a pleasure for me to be here at this school to give presentation with this pretentious title, but I hope that I will at least manage to give justice to the main, let's say, milestones of the history of quark-gluon plasma over the last, as you will see, 50 years. Now we are in the 51st year. Now, and this is my starting point. My starting point is actually subnuclear particles. This is a chart with the year of discovery of subnuclear particles. And well, as you know very well, we start with the electron still 2 centuries ago. And fantastico questo. A baryonic, not a photonic, but a baryonic pointer. And then we have the proton in the tens still, and then the neutron, the positron in the 30s, then the muon, then the war. Nothing happens for a while. As soon as the war is over, then pions, kaons, and then more pions, more kaons, neutrals, V0, lambda, sigmas, xi's, and then it really started to explode. This chart stops at the mid-60s, okay? Now, at that point, the usual story goes that it was clear that they could not all be elementary. Not all these particles could be elementary, so there was clearly something going on. But there was also another viewpoint, which, as you will see, we know today to be wrong, essentially, but it was fundamental for the start of the physics of the quark-gluon plasma. And this was the bootstrap. The bootstrap approach was essentially a very much 60s idea, you could say. It was the idea that hadrons are made of hadrons that in turn are made of other hadrons. So in a sense, there is no hadron which is fundamentally more fundamental than the others. It was called the nuclear democracy. This is pre-quarks, and I don't know if you have ever heard of this book or read the book, Fritjof Capra, The Tao of Physics. He takes this idea and runs away with it, and the physics is wrong, but the book is actually very good. It was pioneered by Geoffrey Chu in Berkeley, of course, California. This is very much a Californian idea, into a theory of strong interaction, the S-matrix theory, and then by Rolf Hagedorn at CERN, really into a theory, a quantitative theory to calculate processes. This was not just a, let's say, a fancy idea that people were trying to make work. Rolf Hagedorn was not working in the theory division at CERN. He was working for the machine. He was working for the accelerator. So this theory was really used to calculate the processes that were needed for the machine, for the machines to work. And indeed, it was very successful. There is this atlas of particle spectra, which is calculated by Hagedorn and collaborators in 1970. And basically, how was it calculated? Processes were calculated based on hadron exchange. So you, as today we exchange bosons in quantum field theory, this was a similar process based on Feynman diagrams where what was exchanged was hadrons. Of course, there is a catch, and the catch is that you have to know about all the existing hadrons, because you can you can exchange hadrons that you have already discovered and hadrons that you have not yet discovered. And this is where Hagedorn comes in, because he had calculated the spectrum of hadron masses by this equation, which is the bootstrap equation, so the density of hadrons with a mass m, which had this dependency, mass to the minus 3, e to the m over th. This th is, and you will see why in a minute, is what is called the Hagedorn temperature. And the value that was used was 150 to 160 MeV. And as you can see, the thing works rather well. The blue is the expected spectrum density as a function of mass, according to the Hagedorn bootstrap equation. The green are the states that were known in 1967. The red are the states which were known by the mid-90s. There is also a more recent version which goes even nearer, but as you can see, the equation itself works very well. And actually, you get very similar results from lattice QCD. There is actually a 2010 paper by Majumdar and Müller that comes to a very similar result. So that is why the bootstrap theory worked well for hadron interactions in the first place. So the idea was deep, even if the physics was not fundamentally the correct one. Why am I telling you all this? Because an initially hidden consequence of this equation is the limiting temperature for a system of hadrons. This is the partition function for a system of non-interacting pions. And then this, you can use it as a starting point, as a proxy for a system of hadrons. And then you can introduce interactions as resonances in the gas, so that an interacting system of pions becomes, in the Hagedorn formalism, a non-equivalent to a non-interacting gas of all possible resonances. And then you can write this sum of partition functions. And if you insert the Hagedorn bootstrap equation in the equation, then you find this expression, you simplify to an integral, and this expression, this is the temperature and this is the Hagedorn temperature, and it diverges as T, as the temperature tends to the Hagedorn temperature. So the conclusion there, and this was made explicitly, was that there was not only an absolute zero temperature, but a maximum temperature, which was this 150, 160 MeV, the maximum possible temperature in nature. This, as I say, was pre-quarks, but then the quarks entered the scene. That was the other main idea to explain the multitude of particles which were being discovered. The eightfold way is from 1961, the quark hypothesis 65. Partons in deep inelastic scattering were observed in 1968. At that point, we had up, down, and strange. Then in 1970, the Jim mechanism was introduced, Glashovilopoulos and Mayani, to explain the existence of flavor change in neutral currents. This was postulating the existence of the fourth quark, the charm quark, to cancel these flavor changing terms in the Lagrangian. And then in 1974, charm was discovered with the observation of the J psi at Brookhaven and Slack, and then Frascati 5 days later, so Frascati didn't get the Nobel Prize. At that point, the quark hypothesis was widely accepted, and in 1975, then, there was this famous paper that Enzo was referring to, the Cabibbo-Parisi paper, and the idea essentially is very well explained in the abstract, which is very small, but I will read it for you. The exponential increasing spectrum proposed by Hagedorn is not necessarily connected with the limiting temperature, but it is present in any system which undergoes a second-order phase transition. At that time, talking of second-order phase transition. We suggest that the observed exponential spectrum is connected to the existence of a different phase of the vacuum in which quarks are not confined. So, in other words, the Hagedorn temperature was understood as not being the maximum attainable temperature, but to be the maximum attainable temperature for a system of hadrons. And then beyond that the quarks and gluons would be deconfined. This was the phase diagram, which was drawn by Cabibbo and Parisi. Interestingly, the first one had the temperature on the x-axis and the baryon density on the y-axis. This is a modern, let's say, still artistic view of the same thing, but from then on, temperature has always been on the y-axis. There was the other paper that Enzo was referring to, Collins-Perry, and this was essentially, now, in a sense, Cabibbo and Parisi were going to the high temperature, Collins-Perry were going in their formulation to the high baryon density. So what they say is that here again, the basic argument is very, very intuitive and simple. A neutron has a radius of about 1 Fermi. So has a density of about 10 to the 15 grams per cubic centimeter. Whereas the central density of a neutron star can be as high as 10 to the 16, 10 to the 17. So 1 or 2 orders of magnitude. In this case, one must expect the hadrons to overlap and their individuality to be confused. Therefore, we suggest that matter at such high density is a quark soup. This was 1975. The name came only in 1978. It was introduced by Ed Shuriak as Quark-Gluon Plasma. So the name is originally a Russian name, which was then translated to Quark-Gluon Plasma in English. But this is the original paper, which is entitled Quark-Gluon Plasma and the Production of Leptons, Photons, and Psions in hadronic collisions. So that's where the state of matter was christened. Fast forward to today, we know the rigorous way of performing calculations is in the non-perturbative regime of QCD, of course, is lattice QCD. So equations are discretized on a space-time lattice, and this takes care of ultraviolet divergences. And then the limit is taken to the lattice spaces going to 0. And this is a typical result. What you see plotted here is as a function of the temperature, the energy density, the pressure in blue, the pressure in red, the entropy density in green. In all cases, this is divided by the Stefan Boltzmann behavior with T to the 4 or T to the 3 for the entropy density. And one sees that there is a rapid change around the critical temperature of these quantities, which is due to the fact that now the energy can be distributed over a much larger number of degrees of freedom. The critical temperature, so today's equivalent of the Hagedorn temperature, is now calculated rather precisely on the lattice, 156.5 plus or minus 1.5, which corresponds to energy density in the order of the JeV per cubic Fermi. This is an enlarged version of the phase diagram that I showed before. So we have here the net baryon density, the temperature on the y-axis. We think that in the early universe, there was a phase transition from quark-gluon plasma to hadrons very close to the y-axis, because there is a very we think that there was a very small excess of baryons over antibaryons at the Big Bang, whereas in neutron stars, one would undergo a phase transition rather close to at the collapse of the star, rather close to the x-axis, from the hadronic phase to the color superconductor and the deconfined matter. Now, this is, of course, the physics of confinement of deconfinement. First of all, it's very interesting in its own right, but it is also very much connected to the physics of the masses of the hadrons, and in particular of the baryons and nucleons. In the case of the nucleon, if you take the Lagrangian mass, 2 up and 1 down for the proton, you get to about 10 MeV. So we know that a proton weighs about 1 GeV. So there is about 99% of the mass of the nucleon, which, as we know very well, is generated dynamically. This is actually the only experimentally accessible phase transition in a quantum field theory, for now at least. And it's, of course, very closely connected to the Big Bang evolution, where, as I said, this transition happened very early. The estimate is about 10 microseconds or so, and is connected to the structure of compact stars. What do we do? They can interrupt at any time. Huh? Feel free to stop me. I mean, in a fundamental quantum field theory, not in an effective one. I mean, in the standard model. Yeah. The no, the lattice is related on quarks and gluons, not in a hadron resonance. Ah, vabbè, this you. There is no limitation. Principle. They put their masses and they say there is a gas of these particles, what's their behavior? Where you are probably right is that if one had the full spectrum, that would fail, but we don't have it. Okay, so let's go on. By the 80s, the hunt for the phantomatic Quark-Gluon plasma was on. The idea was, how can we access this in practice? How can we create in the laboratory the conditions for producing this state of matter? And now, the nuclear physicists at the time heavy ions to study Coulomb barrier shock waves in collisions between nuclei at GSI, but also at Berkeley and even in Dubna, in the then Soviet Union. And it was realized that nuclear collisions could actually, if one could increase the energy of the collision, could provide the conditions for QGP formation. So the idea was to go to higher energy colliders, or at that time it was still fixed target accelerators, and try to accelerate nuclei, try to accelerate heavy ions. And this was started in the 80s at BNL, at the AGS, with oxygen and then silicon, and then the truly heavy gold. And in parallel, at the SPS at CERN, at higher energy, again with oxygen and then sulfur in that case, and then lead starting from 1994. This is a chart which I will not go through, but it shows you the many experiments that were performed at the SPS. And these experiments came in family of somehow the collaborations started. All collaborations started from reusing existing equipment and then made more and more specialized layouts, and the program started in 1986, and then it continued into the 2000s. I will cover essentially up to the lead. Now, the first thing that people tried to do was to understand if there really was a quark-gluon plasma phase which was formed during the history of the collision. And this was not trivial, because everybody, of course, knew that even if the temperature, the conditions for deconfinement were reached during the collision, of course the system would have expanded and cooled down, and then we would have found ourselves back with hadrons in the detector. So people started to think about the signatures that the passage through the quark-gluon plasma phase could have left in the history of the collision that could still be detected in the final state. And there were two major proposals in the 80s. One was Strange's announcement, and one was J-psi suppression. And I will now tell you a few words about each one of these. So Strange's announcement, the idea here was that in the quark-gluon plasma, and I didn't go into the details of this, but essentially one thing that happens is that the values of the mass, I told you implicitly that the way the mass of the hadrons is generated is dynamical, and most of the mass is generated at confinement by the confinement mechanism. What was expected for the deconfined phase was that the quarks that you see in the deconfined phase would be the bare quarks, the quarks of the Lagrangian, not the dressed quarks of QCD. And in particular, it would have become much easier to produce strange quarks, because the mass of the strange quark would have gone down from about 500 MeV, which is the effective value inside the hadron, to 150 MeV, which is the Lagrangian value of the strange quark mass. So copious production of, and at that point 150 is similar to the temperature, so it's something which can be reached thermically in the system, in the quark-gluon plasma, because by definition the quark-gluon plasma would be above the deconfinement temperature. And this was number one. And number two, the effect would be amplified for particles with multiple stranges. And this was the prediction of made by Rafalski and Muller in 1982. I take the paper away so that you can see fully this. Essentially, if you have a hadron with one strange quark, it has a certain enhancement. If it has two, you have the square, and if you have three, you have the cube. And 3 would be the omega minus, and this is the pattern, this is the legacy pattern from W97 and A57. What is shown here is the enhancement as a function of the number of participants, essentially, of nucleon participating in the collision. And you have lambda, psi, omega plus anti-omega, and then anti-lambda, anti-psi, omega plus anti-omega, and then lambda and psi. These are separated because this is a fixed target experiment, so baryon number tends to go in one direction, which is the direction where the experiment measures, so it's good practice to keep them separate. But essentially, these particles, anti-lambda, anti-psi, and omega plus anti-omega, have no quark in common with the incoming nucleon. And you see that the effect is there. It is very large. The enhancement goes up to a factor 20 for the omega. So it increasing with the strangeness content and increasing with the number of participants in the collision. So one signature was there at the SPS. The other was the J-psi suppression. This was proposed in 1986 by Matsui and Zatz. Essentially, the idea is, I have it? Yes, I have it. So the idea is that these quarkonium states and bottomonium states in the plasma phase would be suppressed, because essentially you would have, what is a plasma? A plasma is free charges. So inside the quark-gluon plasma, there would be free color charges. So the field would be modified in an analog way as to what happens in an electromagnetic plasma, where you have a Debye length beyond which the potential is screened. And what you have in this cartoon is, as a function of the temperature, you have the Debye length, and you have the value of the radius different quark-gluon states. So you would expect at a given temperature that all the less bound quark-gluon states, so states which have a radius which is larger than the Debye length, would not form and would be melt. This is again the legacy plot from NA50, from the NA50 collaboration. What is shown here is the measured over expected J-psi suppression. The complication is that even for a purely nuclear system, hadronic system, you do expect to have a certain amount of suppression in the production of J-psi because of interactions of the J-psi with other particles which are produced around the collision. So that's why you have to go to this more complicated way to see the effect more clearly. And what you see here are different collision systems as a function of the energy density. So you have lead-lead in red, and then you have lead-lead. You have two different lead-lead samples, actually three, and then you have sulfur-uranium and proton-lead. And what you see is that when you get to an energy density which is of the order of 2.3 J per cubic Fermi, you have this additional anomalous, as it is called, J-psi suppression, which then increases very swiftly when you go to more and more central collisions. So the two, then there were many more observations, of course, which were made, but let's say that these were the two key points that were used as a basis for the press release that was made at CERN in the year 2000, announcing the discovery of a new state of matter, which had, that was the wording at the time, which exhibited many features of the sought-after quark-gluon plasma. That was what was happening on this side of the Atlantic, but there was a lot which was being prepared on the other side of the Atlantic in the US, and it's worth to look a bit at the history, because the development of what would have become then the RIG program was due to a very interesting stellar alignment of different situations in the US. The starting point is that in 1978 there was a project approved at Brookhaven, which was called Isabel. This would be a proton-proton collider, so two rings, not a proton-antiproton, but proton-proton at 400 GeV. It was the aim of the project was to look for the W and Z bosons. But the same year, at the same year, there was the approval of the transformation of the transformation of the SPS into a PP bar collider at CERN at an energy comparable, a bit higher than the one of Isabel. And Isabel started in earnest, but it ran into problems rather quickly. In particular, the production of the magnets ran into problems in 1981. And actually, of course, the transformation of the SPS into a collider was much quicker because the SPS already existed. Isabel would have had to be built from scratch. So in 1983, the W was discovered and the Z0 in May. And this infuriated the American community. There was this very interesting editorial from the New York Times: Europe 3, US not even Z0. And actually, the effect was striking, because that was the Z0 was announced in May, and in July Isabel was cancelled. But in the very same month, there was an NSAC. This is the advisory committee because it was closed last year. In August, they closed the NSAC. They restructured the DOE. The NSAC was meeting in Aurora in the same month, and the idea was discussed to use the infrastructure of Isabel, which in the meantime had been built to a certain extent, to build a relativistic heavy ion collider. And that is how the RIC started so quickly, because the Isabel was stopped. But actually, even before that, when I was preparing this material, I found that there had been in 1981 a symposium where already the idea of using Isabel at that time to do nucleus-nucleus collision had been floated by Bill Willis, who is one of the fathers of this field. So what happened is that, to put things back in perspective, in 1986, heavy ion collision started at the SPS, and in 1997, the RIC R&D started. Construction started in 1991, and in 2000, the first collisions. And this came with an explosion of results and of knowledge of the many features of the quark-gluon plasma. Here, for reasons of brevity, however, I will concentrate on the two which at the time were the most striking for the community. This is, by the way, an aerial view of the zone of RIC. I remember that at the time when RIC was being constructed, I went to visit in Brookhaven, and they told us a very nice story. This ring is not underground; is on the surface. So it's just, of course, it's covered, but it was built on the surface, and you can see it. Okay, today you can see it very easily on Google Maps, but at the time there was no Google Maps. But you could see it from above, from a plane. And at some point there was somebody that flew over, some American politician who flew over. They didn't know what it was, and he asked the administration, and they didn't know what it was. But then they asked the Russians. Apparently the Russians knew what it was. But the American administration, at least the people they asked, of course, somebody in the American administration did know, but not your ordinary politician. So back to physics. One striking, the first striking measurement actually to come out of RIC was the measurement of the azimuthal asymmetry. Now, the azimuthal asymmetry is crucial. Is a crucial diagnostic tool in this business, because essentially it gives us information on the amount of collective effects in the system, in the colliding system. Basically, the geometry, the generic geometry has this. You of course don't have to tell you. I think you guys are experts. But let's say if you imagine that this is an incoming nucleon, this is the nucleon which is coming out. So this is going in, this is going out of the screen. For instance, the superposition region has this almond shape, and the extent to which this asymmetry, which is a geometrical asymmetry, is transmitted to momentum space gives us a measure of the strength of collective phenomena. You can convince yourself of this very easily. If you have a very large mean-free path, basically you will have your partons flying out without any memory of the collision geometry. But if there are interactions, if there are collective phenomena, then of course a particle going out in this direction will see a much larger pressure gradient than a particle going out in the other direction, and therefore in the extreme case you will have zero mean-free path, which is what we called, is another way of saying the hydrodynamical limit. And actually what was observed is that indeed the asymmetry was as large, at least at low transverse momentum. This is one of the early measurements from Rick, from the STAR experiment, until a momentum of 1 GeV or so. The black are the measured points, and the green is the hydrodynamics calculation. And what is measured is the V2, which is the first non-trivial coefficient, let's say, of the Fourier transform of the azimuthal distribution as a function of Pt. And this is the origin of the expression of a perfect liquid or almost perfect liquid, ideal liquid for the quark-gluon plasma. Comes from the fact that this is where the bulk of the particles is emitted. Below 1 GeV you have more than 90% at Rick. So this is essentially where particle production happens, and it is essentially at the hydrodynamic limit. And this was one crucial piece of support for the QGP picture because of the hard equation of state. And the other was the nuclear modification factor. Do I need to introduce? I will introduce the nuclear modification factor. Let's do it. Okay, so this is a sketch of a collision. This time one nucleus comes from the left, one from the right. And here you see this sketch gives you the nucleons, depicts the nucleons which are in the superposition. Okay. You can count the participants as one does for soft phenomena, and you can see that in this particular sketch there are 7, or you can count the binary collisions. So how many times a parton from one nucleon of one of the nuclei sees a parton from the opposite nucleus, and then these are, in this particular case, are 3 by 4, they are 12. So for high PT phenomena, for hard phenomena, you expect them to scale with the number of binary collisions, and therefore what you can do is create a variable which is called the nuclear modification factor. This is given, in, for instance, in the case of the PT distribution, in the nucleus-nucleus collision. PP, and you just have to scale the PP distribution by the number of binary collisions. And in principle, if there is no nuclear effect, which in this context means no effect which is connected with the fact of using nuclei instead of protons, you would expect this to be at 1. And indeed, this is what you find for photons or Zs or Ws. And instead, what you find is something like this. This again is one of the early measurements, the first one that I saw at least. And you see, these are different centrality regions, so centrality collisions. Centrality means a small centrality means that there is a large superposition between the two nuclei. High centrality means that the superposition is small. So when you go to very peripheral collisions, so high centrality, you have essentially the production of high PT particles. It's rare, but there are high PT particles. You have it essentially at 1. Of course, you never expect this to work for the soft regime, so you have to you have to look out here. And then, as you go to more and more central collisions, you start deviating, and you get the maximum deviation for the most central collisions. This is interpreted as due to the energy loss of partons before they hadronize. So a high-PT parton tries to escape the plasma. It is slowed down by this charged medium, color charged medium, and this energy loss results in a loss of particles at high transverse momentum and a moderate increase at lower momentum, so a peak somewhere at in the mid transverse momentum at moderate PT. This is something that goes with it. What is shown here is the delta phi distribution. Essentially, these are two particle correlations. So you trigger with a high PT particle and you look at particles around it. You plot the angle, and if you look at proton-proton, which is the black, or even deuteron-gold collisions, you see that there is the peak close to delta phi equals 0, because we know that these particles tend to be produced somehow in a jet or a mini jet around the direction, the original direction of the parton. Then you have something on the opposite side, which is usually broader because of the nature of the particle production itself, because it's not precisely back to back. And then you see that if you go to central gold collision, the away side peak essentially disappears. The near side peak has to be there by construction. So this is another indication that the loss destroys the jet essentially. So the overall understanding that emerged from Rick was significant, because as long as we were at the SPS, we were seeing the quark-gluon plasma somehow in our minds as a sort of gas of quarks and gluons. In retrospect, there were already indications at the SPS, but most of us didn't catch them. Whereas at RIC, it became clear that the quark-gluon plasma was very strongly coupled. And from there on, we speak of the SQGP, of the strongly coupled QGP. How am I doing with time? Very bad. Okay, let's see. Now, meanwhile, in Europe, things were also moving. In 1989, there was an LHC workshop in Aachen, where the physics case was first made for a heavy ion program at the LHC. And then there was an expression of interest for a heavy ion experiment in 92, letter of intent in 1993, technical proposal in 95, and then in the 2000s, the construction. And in 2010, there were the first lead-lead collisions at the LHC. Now, it's the environment of the LHC is unique for this physics. The conditions are almost ideal because at central rapidity, essentially, there is no baryon density, even less than at RIC. And this is close to the conditions of the Big Bang, but also from the theoretical point of view, the lattice QCD calculations are much more reliable. The LHC is an excellent collider of nuclei. The luminosity is very high, and one can do even asymmetric collisions, including proton lead, in spite of the fact that you have only one magnetic field in the machine to work with. If you are interested, this is a very interesting issue. We can discuss it. There is abundance of calibrated probes, hard probes, because the energy is very high. You have a few hundred of CC bar pairs per event produced in a central lead-lead collision at the LHC, for instance. And state-of-the-art detectors. The dedicated experiment is the ALICE experiment, which is essentially optimized for this physics, but also Atlas CMS and LHCb are participating in the program. Now, the ALICE experiment, I will go quick here as two main parts. There is a barrel and a muon arm. The important thing is that you need to have very low material and very good vertexing, because you want to measure soft particle production, because the bulk is soft, and because you want to catch heavy flavors, which, as we will see, are a key tool for this physics. So charm and beauty particles. We have had a series of collision systems, and lately also oxygen, and proton oxygen came last year, and even a bit of neon came into our collection. Now, the first thing that you can look at is integrated yields, and this is very impressive. You see these are the yields of different particles, and the measured values are, these are PT integrated, so essentially how many of each type are produced in our rapidity window. The balls are the measurements, and the lines are what you would expect for an equilibrated gas at a temperature which here is used essentially. What we use here is the critical temperature, 156. This works very, very well. There are a few deviations. This is the deviation in sigma, but by and large it works very well, which means that hadrons are produced essentially at thermodynamic equilibrium. This is not the case in proton-proton. In proton-proton we are very far from chemical equilibrium. And this is another way of looking at Stranger's announcement, in a sense. And there are some deviations, but and they are very interesting, because deviations from equilibrium carry a lot of information. If you are interested, we can discuss it. And this works even for nuclei and hypernuclei. This is amazing, because essentially we are at the phase transition, so it looks like there is an explosive hadronization with somehow the yields being determined at the freeze out, very close to where the phase transition happens. And this works even for nuclei and hypernuclei, in spite of the fact that they have a very low binding energy. So nucleus at the LHC is essentially a nucleus factory. And yes, it's no, it's there. These are the protons, and these are the antiprotons. So it's there. It's about 3 sigma. Well, GSI Heidelberg, they have they have more screws that they can turn. But yeah, Thermus is about a 3 sigma. And yeah, this I already said. Now, another thing that happens at the LHC is that there is a very large multiplicity of particles produced. So one can do not only V2 but also V3, V4. Here there is some early example where one gets up to V8, but now we can go even higher than that. And this is very nice, because one can basically, if you look at this event, normally you would expect to have a V2 just from the geometry, but then, as is depicted here, event by event, the nucleons don't have to be distributed uniformly. You can have fluctuations, geometrical fluctuations, and you can have events that have more of a triangular shape in the superposition zone, once you take into account where the nucleons physically are, etc., etc. So essentially, you can map how the system responds to initial state fluctuations, and this, of course, is very rich in terms of informations on the physical quantities underlying the system. And this is somehow one way to see this on the other side, so on the side of the extraction of the physical parameters, this is an example of what we call a Bayesian method, whereby one takes different models of the collision and tries to use the data to constrain the parameter, essentially by doing multiple calculations with different values of the physical parameters. And this is the result for the viscosity of the QGP. This is the shear viscosity. And now we have it at about 20% precision, which I think it's already impressive. Of course, we want to do better than this, but from a system of hadrons being able to calculate to 20% precision the shear viscosity of the QGP, I think it's quite a feat. But as I was saying, heavy flavors are the true gold mine, in my opinion, for the and in the opinion of most of us in the collaboration, I must say, to get to the physical properties of the medium in a quantitative way. This is a collection of nuclear modification factors. So you have in red, you have the pions, you have the Ds in black. You have the J psi here in green, and then you have this is divided into prompt and non-prompt J psi. So prompt J psi is in magenta. Prompt means that it's produced at the primary vertex. Non-prompt is in blue and means that it's produced in a beauty decay. And what you see is that there is a clear hierarchy. So you have pions, charm, and beauty, in a sense, which are suppressed in different ways. So you have a sensitivity to the mass and to the color charge. The mass, because if you have a heavy flavor particle, you know that the mass was the mass of a charm quark or the mass of a beauty quark, and you also have the color charge because you know you had to do with a quark and not with a gluon to begin with, unless, of course, in very particular cases where the charm or the heavy flavor pair comes from the splitting of a gluon at higher virtualities. And because mass, the heavy flavor quark acts essentially as a Brownian probe of the medium itself. So you can imagine that you have your medium and you put a large object inside, and you try to get it thermalized and extract the properties of the system from that. Now, we know that they are strongly involved in the flow, so that was the nuclear modification factor, but also the V2, I'm with you in a minute, is significantly different from zero. This is the V2 and also the V3, and this is for central and for less central collisions. Yes? It can. I think it will become clearer in a moment when I will discuss the equilibration, the thermal equilibration of charm and beauty. But then ask again if it's not. So this is the state of the art. This is the nuclear modification factor and the V2. And first of all, this provides substantial model constraints. What you see shown here is a measurement with the same Bayesian method that I showed before of the diffusion coefficient of the QGP. And this is the measurement from Alice data. It's 50% still uncertainty on the measurement, but it starts to be something that one can call a measurement. And of course, we want to go much further than this. There is a new regime for J psi production at the LHC. What is shown here is the nuclear modification factor in black, is the nuclear modification factor at RIC as a function of the centrality of the collision on the left and the transverse momentum of the right. And the color data are from Alice, blue and red are two different data sets at two slightly different energies. But what you see is that qualitatively by eye it's very different. There is a much more pronounced centrality dependence at RIC than at the LHC. And there is a significantly different transverse momentum distribution. It's flattish at RIC. If anything, it goes up, whereas it goes down at the LHC. This squares very well with the following. There are many charm quarks. I already hinted at this a few minutes ago, produced per collisions at the LHC up to a couple of hundred in the most central collisions. And at that point, you have a new mechanism for building a J-psi at the LHC that you don't have, that is not so significant, let's put it like this, at RIC, which is by putting together a C and a C bar quark, which originally come from two different elementary collisions, initial state collisions. And where do you expect this to be more important? At high centrality and at low PT, which is where most of the charm quarks are, and this is exactly what we see. This is the V2 of the charm, and I am coming to the thermalization. Quarks themselves flow. So one could say maybe the Ds have a V2 because they pick it up from the light quark. A D has a heavy quark, and the light quark, maybe you could say the flow, all of the flow comes from the light quark, but it doesn't, because we see that the J-psi, which is purely CC bar, also has a significant V2. So it looks like the charm is indeed heavily coupled with the medium, and beauty, as I already said, is quenched too, but less than charm, which I already shown before. And also beauty flows. So if you look at the V2, this is prompt D and non-prompt D, so B from B decays. And these are the data of CMS. You have the same from Alice, but it's good to vary now and then. And you have a similar trend for V3. So beauty is also strongly coupled with the system, but less than charm. The upsilon states also seem to follow, to have a suppression, and the sequential suppression. So the less tightly bound ones, Y3 and then Y2 and Y1, in order of more and more strongly bound, are suppressed in a very different way. So the most tightly bound is the least suppressed. But the upsilon doesn't seem to flow much, at least within errors, whereas the J-psi has a significant suppression. The upsilon seems to be, at least within the present, there doesn't seem to be, it certainly looks to be smaller than for J-psi and compatible with 0. So could it be that beauty quarks do not flow, and that B get all their flow from the light quarks, what one could have thought for the originally for the Ds. But it's not even clear that the upsilon flow should reflect the B quark flow, because there is not much recombination component expected for the upsilon, because there are much less B quarks produced per event. There's just a handful as opposed to hundreds of charm quarks. Now, it's also not obvious that the upsilon suppression should fill the geometry. Sorry, it's not obvious that the upsilon suppression in any case should not fill the geometry, because maybe just that asymmetry, as the upsilon tries to come out of the QGP, one should see. But if it's there, it's very, very small. So one possible idea is that could there be two populations, say color octet and color singlet, where color octet disappears, color singlet goes through, and maybe does that isotropically. The color singlet is not charged, so in principle you could, this is all very qualitative, but one could imagine that it could go out of the QGP without feeling it. Small systems, the new frontier, a new frontier at least. We have long-range correlations on the near side, which have been measured in proton-lead collisions and even in proton-proton collisions at the LHC, at least in high multiplicity collisions. This is a very nice intuitive way of looking at it from CMS. This is a lead-lead collision. You have on the near side, you have this is delta phi, delta eta correlation. So delta phi here and delta eta in this direction. So basically, this is the delta phi distribution. So you have the near side peak, which I showed before with some early RIC data, and this is the away side peak, the peak of the recoil. And you see that you have this elongated structure on the near side, which you do not have in proton-proton collisions. So you have the jet peak, but you don't have this structure, this long-range structure. But some structure starts to emerge for high multiplicity collisions. This is another way of looking at the V2, because the V2 is just the two-particle correlation, the first manifestation of two-particle correlations. The V2 is the first non-trivial coefficient. And in fact, what we did was to do it in a slightly different way. So here you have the high multiplicity and the low multiplicities are now ALICE data. This is proton lead. You see it's a bit less evident because CMS has a larger rapidity acceptance than ALICE. But when you look at the data, you see it clearly if you calculate the correlation that you have a ridge here. We call this ridge at high multiplicity, and you don't have it at low multiplicity. So what you can do is to subtract low from high, and you see two peaks which have the same height. So basically, and you can also see that this goes up and down. They go up and down together as you change the multiplicity. So truly, this is a manifestation of the V2. You can interpret it as a V2. And for instance, you can do the same exercise with using identified particles. And when you use identified particles, let's start from the lead data, you have a very characteristic behavior. Basically, at low transverse momentum, you have particles of different mass which act in a different way, just because this is the result of having a common expansion velocity, which of course pushes further in PT particles which have a higher mass. So you have a clear mass ordering, whereas if you go to high transverse momentum, you have a baryon meson baryon splitting, and this is due to the fact that at hadronization, if you produce your mesons and your baryons by putting together valence quarks, essentially, this is the intuitive way of looking at this, even if it's not fully rigorous, but by and large it works, because you see that if you need 3 or if you need 2, you have a different behavior as a function of PT, because you can use you can be at the same PT with 2 in the case of mesons, and you can use 3 to build the same PT in the case of baryons. So you have this decisive split, and you have exactly the same behavior for high multiplicity proton-proton collisions. So it looks like even in small systems at high multiplicity there's something going on. This is not the only thing that goes on. There is also strangeness enhancement in high multiplicity proton-proton and proton-lead collisions. These are the lead-lead data at high multiplicity. So these are the omega, psi, and lambda. This is now plotted in a bit of a different way than what was done in WA97. This is now the ratio to pions. Is another way of looking at it, but basically you measure the enhancement from low to high. So still same effect. The highest enhancement is for the omega. But what you see is that it goes very smoothly from low multiplicity to high multiplicity. You can almost dial in the amount of strangeness enhancement. It's not reproduced by models. By now, they start to reproduce some of this data, but then, for instance, if you try to get the omegas, you destroy, in PITIA, you destroy the protons, so you cannot get the full picture together. We don't know what it is yet, it's fair to say. It could be that simply in high multiplicity proton-proton there is QGP formed, or that it's some sort of precursor phenomenon. I don't think that one will go from non-QGP to QGP without going through some kind of gluey way of partons feeling one another's present. But the important thing here is that this has opened a completely new direction of research, because indeed we can tune in the amount of collectivity, and we can now use PP event generators to study the phenomenon. There are these effects, but there is no experimental sign of quenching yet in proton-proton collisions. This is the present status. This is for pions, pi zeros up to 200 GeV. Same thing for heavy flavors. We are getting much more precise data now, but basically for D mesons there is no indication of quenching, and this is another puzzle I find, because the flow seems to be there. I showed you. Even in for proton lead I didn't show it, but I show it now. So for proton lead there is a V2. Also for the Ds, the red is the Ds, the other are kaons, lambda, psis, and omegas. And we think that the charm is produced in these collisions isotropically at the beginning of the collision, okay, without knowing what the geometry is. Now, if it turns out to be isotropical, non-isotropical, which is another way of saying it has a V2 different from zero, it means that somehow it has felt the geometry of the medium. So it has interacted with it. So one would, somehow one is bound to interpret this as a sort of sign of azimutally dependent energy loss. Could it be, once again, just the light quarks? No, because the J-psi also does that, okay? So the J-psi itself has a V2. So is it consistent with the RP-LED measurements? Quantitatively, I guess it is. But okay, maybe once again, if V2 is due to energy loss, it may carry information on octet versus singlet for the J-psi. The jury is out. We have to wait and see for more precise data and more targeted calculations. Beauty is the odd man out. Once again, beauty is different. The V2 of beauty seems very close to zero. So this is another indication that beauty seems to be far from completely coupled with the system. I will skip this. These are data from light ions. This I put it because it's here, because it's very topical. Basically what you have here is the nuclear modification factor from proton lead in green, and then you have lead in red, and also xenon in blue, and then the black points are the oxygen which were measured just this spring. So it's somehow in the middle between the two. This is the comparison with some calculations. The blue one has just nuclear PDFs, and the red ones has also some energy loss. We are somewhere in the middle. Stay tuned. The data is very precise. We will have to see how the interpretation from the theory evolves. This is just a link to the full review of Ali's results for completeness. And now in the rest of the time, I would like to go to our plans for the future, which are the most interesting part of this talk, I think. This is the long-term schedule of the LHC, and I have the wrong one here. Okay, I will I will put the correct one, but because okay, we will go on and run a bit also this year. But basically, there is now a long shutdown. Then there is there will be run 4, another long shutdown, and then run 5, which will actually extend out to 2041. Remind me to correct this. No. So run 3 started in 22, run 3. And run 4 will start in 30. Yeah. Okay, so what we want to do is for LS3, for long shutdown 3, is two things. One is to improve further our vertexing. This is the point in resolution. In blue is the current one, and in red is the one we want to reach with this new version of the inner tracking system in ALICE. This is translates non-linearly. It's very much amplified when you look at heavy flavor particles, because it's the power for separating a secondary decay from a heavy flavor particle from a primary originated particles goes very non-linearly with this power. So this will result in a huge improvement. This is what we expect for the RAA of the B sub S, for instance. And the main goal is to get much more precise for rarer heavy flavor particles, basically. And then we have a second upgrade, which we call focal forward calorimeter, and this should be sensitive to gluon saturation in proton nucleus collisions. I will not spend much time on this, but let's say this is different experiments which will come online. This is also the LHCb, the new LHCb upgrade. This is forward measurements at RIC. This is the EIC, and this is what we expect from the focal. So it's the planned experiment that will give us the highest reach at low X to a few 10 to the minus 6. But the new frontier is what we call ALICE 3, which is essentially a new experiment, a new apparatus. Is a compact all-silicon tracker with a wide rapidity acceptance, a high-resolution vertex detector, a new superconducting magnet system, hadron, muon, and electron identification, and we also plan to have a forward conversion tracker. Now, the key to get the maximum possible precision on the measurement of heavy flavor is to go as close as possible to the primary vertex, and as close as possible at the LHC means 5 millimeters. This is the closest you are allowed to go to the beam. Nobody has done that. There is a system in LHCb that goes very close, but it's not a barrel detector. So basically what we need to do is to go inside the beam pipe And the problem is that when the beam is injected, you cannot stay at 5 millimeters. You have to stay at 15, 16 millimeters from the beam. So we need a movable system that stays open at injection, and then when the beam has been accelerated and is stable, and then can close. So you need a geometry like this. So you inject the beam, you accelerate, and then when it is stable, you close your detector on the beam. This is another way of looking at it from the side. This is a way of doing it. We call this the iris. It's similar to what your camera does when it opens and closes the lens. I will just give you a personal favorite of the physics that one will be able to do with this apparatus. So one is low PT beauty. As I said before, beauty seems not to be fully equilibrated. It's less suppressed than charm. There is less flow. And in general, I didn't show that actually, but take it from me for now. No, maybe I have something later that will show it. The statistical hadronization model seems to fail for beauty. Now, the relaxation time of beauty is 3 times lower than that of charm, simply because the relaxation time depends on the diffusion coefficient and is proportional to the mass. And the mass of beauty is 3 times the mass of charm. Now, this by itself doesn't imply that B cannot fully equilibrate. It depends. Given a system which is large enough and lives long enough, it could fully equilibrate. But it looks like, experimentally, it doesn't. So it looks like at the LHC, with the even central lead-lead collisions, charm seems essentially equilibrated and beauty does not. So in a sense, we have been lucky, because with charm, we can see how a flavor which is kinetically almost completely equilibrated behaves, and then beauty gives us the handle to study somehow equilibration on the move, as it were. But for doing that, one needs to go to very low PT, down to the diffusion regime for beauty. And this will need Alice 3. Another thing which we want to measure with Alice 3 is multi-charm. And this could really be the final frontier for studying the behavior of heavy quarks in the QGP. There is a huge announcement which is predicted for particles with multiple charm up to a factor 10 to the 3 for the omega CCC, for instance. Basically always for the same reason as charm, although the situation is different. But still, the idea is that if you want to make these particles in proton-proton collisions, it's very hard because of this reason, because we have negligible production of Xi-CC or omega CCC in single parton scattering. Whereas if you can build your particles by recombination of partons, then it becomes much easier if you have a quark-gluon plasma. And these multi-strange particles are essentially purely recombination particles. Okay? Unlike the J-psi, because for the J-psi, we know that one can produce J-psi. Actually, it's not very well understood even yet, the production of J-psi, but we know that J-psi are significantly produced even in single parton interaction. Whereas, and I finish on this slide and then I'm with you, a factor, it's not just, 10 to the 3, hey, let's go for it. It's that such a very large effect will be very sensitive to the level of equilibration of charm itself. So it will give us a handle to measure by how much, maybe in different event categories, charm is near or far from full equilibration. Because in the end, the aim is that we have to be able to describe charm equilibration and beauty equilibration, or even better, charm deviation from equilibration and beauty deviation from equilibration with the same parameters, so with the same diffusion coefficient. Yes.
Is a nice way to study the equilibration time, right?
Well, yes, in a sense, yes, you can put it like that.
One can understand when the hydrodynamic behavior emerges or goes out of the picture through the study of beauty.
I think so. This is I'm an experimentalist, okay? So I'm very naive, but it seems to me that, in a sense, yes, because everything points to charm being very close to equilibration. If you are fully equilibrated, you lose a lot of information about what has been going on. Whereas if charm is not if beauty, sorry, is not equilibrated, then it has to be much more sensitive. Maybe in different event categories, it must be much more sensitive to what's going on in the system. So to the physical parameters of the medium, and to even geometrical differences event by event. So yes. I think it should be better for measuring the physics of the medium, because a lot of information must be lost when you fully equilibrate. DD bar correlations are another. This is a very nice measurement, I find. Now, what do? You essentially, the D and the D bar will originally be produced, will tend to be produced back to back. They are not exactly back to back, but by and large, there will be a very strong anticorrelation. And this can be calculated and taken under control. And then what you can do, if you measure the two, if you measure the D and the D bar, of course, you will have to associate the D bar to its own D statistically, because you have many Ds per event, but we know how to do these things. This can be done. And then one should be able to correlate the energy loss with the angular decorrelation. So essentially, this is the Rutherford experiment on the quark-Gluon plasma. And you can do this as a function of the scale. So for instance, you will be able to see collisional versus the relative importance of collisional and versus radiative energy loss at different momentum scales. So this is bound to be a very precise way of characterizing the system. Charm diaper, this is, I think, the only slide I have on hadron. Yes. This is background subtracted. No, no, because you lose the correlation between the forward and the backward. You completely lose it. So you would expect, this is what you expect if there is no effect. If there is no effect, okay? This is what you expect theoretically with no quenching. Okay? And the points are the simulation of what you will measure in ALICE 3. Now, this could go completely flat. It's nothing to do with the V2, because you correlate the D with its own, with the D bar.
Yes, but if both of them are fully thermalized, they have completely lost the memory of the initial correlation, and they should be both correlated to the reaction plane.
But that you can, that you take into account. Yes, yes, that you can take into account. Yeah, this is the only one that I have on hadronic physics, this is charmed hypernuclei. Nobody knows if they exist, of course. I mean, everybody thinks they exist, but nobody knows if they exist at very low atomic numbers. So this would be the charm equivalent of the hypernuclei. Okay, so sometimes they are called supernuclei. For instance, the C deuteron or the C triton. So you have a lambda C taking the place of one of the nucleons. Were first suggested is in the 70s, and nobody knows if they exist. Now, the interesting thing is that if these particles are produced at statistical addition model abundances, one can calculate the yields, and they should be visible at the LHC. And this is the expected performance of ALICE 3. So if the hyper charm, if the in this case it's the C deuteron. If the C deuteron is produced as statistical hadronization model value, this is what we should see. So if we confirm that charm is fully equilibrated by other measurements, for instance by the Xi-CC or omega CCC at the LHC, we either discover it or we exclude the existence of the C deuteron. And then, of course, with femtoscopy, but I didn't go into that, but one can study directly the potential. An old dream is thermal charm. This was something which was already in our mind at the time of the ALICE technical proposal, the measurement of central charm. And actually, it was already something which was in the mentioned in the Shuriak paper. Basically, I didn't go into this, but charm is fully out of equilibrium in terms of the amount of charm which is produced in heavy ion collisions, because it's not produced, it's not cooked in the system at the temperature of 150 MeV. It's produced at the beginning of the collision before the energy is degraded. So it's produced much more abundantly than one would produce in the Quark-Gluon plasma. This is quantified by something which we call the fugacity. The fugacity is called gamma C for charm in central lead collisions is 30. Now, fugacity 30 means that only 3% of charm essentially is produced thermally. But we know that the initial production of charm goes like A to the 4/3, whereas the thermal production goes with A. So if one goes to smaller nuclei, this value should go up. The thermal component should go up. And if you take, for instance, central argon-argon, gamma C is about 15, the thermal component is already 6%. And the centrality dependence and the A dependence of the thermal component and of the initial component are very different. So this is very qualitatively, but I think that this is something that with very high statistics one should attempt to measure with ALICE 3. You would have a component, you would have two components. Imagine, very naive, you have the thermal component and the initial component, and they have very different centrality dependence. And also PT distribution, by the way. And okay, this is really crazy, but since I'm with friends, I can. Low momentum big quarks are slow because they are heavy. So a 10 GeV beta is still 0.9 for a 10 GeV big quark. And since they are not ultra-relativistic, one could have a shock wave which depends on the momentum. So if one takes typical values of the speed of sound in the Quark-Gluon plasma, one would have the following situation, that B is subsonic for a momentum below 3 GeV or so, and then it becomes supersonic at some point, and one would have a P-dependent wake in the multi-GeV range. And this is some very rough calculation that we made with Shuriak many years ago. And okay, it's something to look for, something to look for. Again, at very high statistics, something like this might come into view. There are many more examples of what one can do with a detector such as ALICE 3. I didn't speak of these XYZ state exotic hadrons, which of course will be measured with very high statistics. We want to measure the shine of the QGP, the electromagnetic radiation which is emitted by the quark-gluon plasma in the form of dileptons, or virtual photons. Such a layout will be very powerful for the measurement of fluctuations of conserved charges, and these are very easily relatable to the lattice QCD calculations. We want to look at ultra soft photons. As I said, nuclei, hypernuclei, search for supernuclei. This apparatus, by the way, is also unique at the LHC. So it has windows, even for new physics, which are not completely excluded, where it is very competitive with respect to the other experiments, such as dark photons or the search for axion-like particles. So I think I can stop here. This is the example of axion-like particles, but I will go, well, this is ALICE 3 if we have an electromagnetic calorimeter, and you see that this is the mass of the axion-like particles, and this is essentially the coupling, and you see that we are very much competitive with the other LHC experiment. So my conclusions are this: we have come a very long way from the realization of the possible existence of deconfined matter in the 70s to the exploration of collective effects with sulfur beams, silicon beams. I didn't go into that, but this was before, let's say, the QGP was discovered. Through the discovery of deconfinement at the SPS, the evidence for strongly coupled QGP at RIC, and the LHC harvest, which has started to give us quantitative access to the QGP parameters. And basically, what we are doing now is to draw the plans for the next 2 decades, and of course, our aim is to, on one side, do the somehow leave the legacy from the LHC of textbook measurements on the properties of QGP. But even more important, every time we have increased our depth of vision on the QGP, we have discovered new phenomena in the physics of the QGP, apart from measuring physical parameters. And this is, to me, the most exciting prospect, because in the end, what we are doing is we are studying the condensed matter physics of high temperature QCD. And we know how rich is the condensed matter physics of QAD. So it's obvious that the condensed matter physics of QCD is going to give us many more surprises. And ALICE 3 is a unique apparatus for doing this physics. So stay tuned. The future will tell what we are going to see. Thank you. Yes. Say again? Well, the advantage with beauty is that beauty is heavy, so it's slow. And you don't have to be, if you are ultra-relativistic, you cannot see this effect. You have to be away from the ultra-relativistic regime. That's the advantage of using a heavy quark. A truly heavy quark, let's say. On this side of the Atlantic, we call it beauty.
Sensitive to what is going on during the evolution. Indeed, with charm, we are discovering step by step that the thermalization time is quite smaller than even if there is not full thermalization, but one is quite close to that. But however, for the beauty, really with round 4 you will be able, or even with the last part of round 3, able to do a measurement of prompt B meson down to reasonably low.
Look, yeah, to a certain extent, we can start already. I mean, this is one of the, okay, now for the ATS3, I think I don't have, what I have is the B-sub-S here. You can see this is centered, the lowest bin is centered at 3. So one can already, indeed, with the ITS3, one can already go to low PT beauty, but to get to really high statistics, low PT beauty, the ultimate performance will be with ALICE 3. But already with the ITS3, this is the kind of yeah, after LS3. Is less far, but you are young.
You mentioned this DD bar correlations. Because first of all, how much can you already measure with?
No.
Okay, so only we must wait. But don't you agree that what would be really interesting as a proof of thermalization would be to compare DD bar with DD, because the production mechanism is completely different, and at the end, if you see a similar pattern, it means that really you reach the thermalization.
Yes, but in a sense, that's another way of doing the same thing. You mentioned before the V2, one could subtract that with DD, and that's another way of doing the subtraction. So in a sense, this is a comparison between DD bar and DD.
There are no other questions. We thank Federico again.
Thank you.